In this video, we're going to talk a little bit about how we can take a specific vector function, calculate its derivative, and start to do things like find equations of tangent lines on this particular graph. We'll also then take a look at the 3D plotter to understand kind of how all this is actually coming together in a more visual representation. All right, let's take a look here at example number 2. Take a look at this vector function that we have. I have a 2 cosine t, sine t, and a t for the components of the vector. We saw in the last video that if I wanted to calculate the derivative of any vector function, it's actually unbelievably easy to do. Because to calculate the derivative, you just have to go ahead and compute the derivative for each of the components. So this part A almost requires no work. I answer 3 simple Calc 1 questions. What's the derivative of 2 times the cosine of t? Well, remember that I would leave the 2 alone and just take the derivative of the cosine of t. That would get me sine of t, but negative. Remember that the derivative of any of the co-trig functions always produce something negative. Cosine, cotangent, cosecant all had negative results. Here, the derivative for the sine of t, that's just my cosine of t. And the derivative for t is just 1. Boom, that's it. That's part A. Easiest question ever, right? That's great. We love taking derivatives for vector functions. All right, now take a look here at part B. Can I find capital T of t? Okay, this is interesting. This is where we have to remember what's going on. Let's suppose again that what we have right here is some curve that looks like this, okay? I don't think this is what the curve looks like at all. In fact, I know it's not what the curve looks like, but let's just pretend, okay? Let's pretend further still that this particular curve here is oriented in the following way, right? So it kind of loops around in this order. Well, if it was the case that I found r prime of t, what that tells me is tangent vectors on the curve. But notice that by itself right now, this isn't a vector. It's kind of like a formula to find vectors. So if you were to plug in, say, 0 for t, that would say, go to the spot where t is a 0 and draw me the tangent vector right there. If you wanted to go to where t was equal to 1, you could draw the tangent vector right there. If you wanted to go to where t was a 2, you could get a tangent vector right there. So again, we would have to plug in specific values of t to find these specific red vectors. This is exactly the same sort of thing that happened in a Calc 1 setting. When you found y prime or f prime of x, that wasn't the slope of the tangent line, but it was a formula to help you find the slopes. So what we can notice though about all of the vectors here is that they might possibly have different lengths. And what t of t, remember, is saying, I want to take all of these vectors and ensure that they are length 1. So what we're going to do is try to figure out what I have to divide this r prime of t by so I can guarantee shrink every single vector down so it is length 1. To do that, we know that we just would have to take r prime of t and divide it by its norm. So what we're going to have to do here is actually calculate the norm for r prime of t, even though we don't know what t is yet. We're going to do this in general so we can tackle all the vectors on the curve at once. All right, let's see. I'm going to go ahead here and say that this is, let's see, my r, the norm of the r prime. I'm going to go ahead and write that out here underneath this fraction, and then I'm going to multiply by the r prime of t that I had over here at the side. Just so it's a little bit easier to see kind of the two pieces that are happening here. All right, so for the norm part, remember I calculate that by doing the square root, and then I square each of the individual components. So here I'm going to end up with a 4 sine squared of t. I'm going to end up with a cosine squared of t and a 1. Now actually, if I wanted to here, I can make use of a nice little trig identity, because if I take one of those sine squareds, just one of them, 1 out of the 4, and I add it together with that cosine squared, that will produce a 1. That means that underneath the radical, I'll be left with 3 sine squareds of t, and now plus 2. Of course, that still is multiplied to the vector of the negative 2 sine of t, cosine of t, and 1. So the result here happens to just be one single vector, which I can now either leave in this form, or of course, I could write it as just each of the individual components divided by that radical, which I'll go ahead and write here. Okay. Now, one thing that's important to make sure that we note here or keep in mind here is that while this formula has gotten a lot uglier looking, right, a lot uglier than, say, the formula that we had in part A, we should understand what the purpose of this formula is. Now, if I go to this new formula and I plug in a value of t, like I plug in t as a 1 or t as a 0 or a 2, I'm going to get the exact same facing direction for these vectors, but now they're all going to guaranteed be exactly length 1 every single time. Every single time. So they might have gotten stretched a little bit or shrunk down a little bit, but now if I use this formula, guaranteed length 1. Okay, let's take a look here at the final question here on example 2. Can I use some parametric equations to describe a tangent line to the curve at the point 0, 1, pi over 2? So for the sake of argument, let's just pretend that I have a curve, and right here is the point 0, 1, pi over 2. What I want to do right now is to build a tangent line there, and I can imagine what that tangent line would look like. Tangent line could be something kind of like this. Now, of course, if I wanted to create the equation of a line in 3 space, I know the things that I'm going to need. I'm going to need that direction vector, which is our 3D version of like a slope, and I need a point on that line. Fortunately, the point on the line is already given to me, so I'm kind of good to go with that. But I do need to know the direction vector. Now, the tangent vector at that point should be able to help me out. If I knew exactly the time t that I needed in order to be at this blue point, then I would be able to go back to my r prime of t and actually build that tangent vector. And once I have the tangent vector, I have my quote-unquote slope for this line. So I'll go ahead here and start by kind of narrating what it is that I need to do. I'll say that we need to find when r of t arrives at the point 0, 1, pi over 2. That's what I need to figure out. I need to know what's the t so that I can use my r prime of t to build the direction vector. Okay, well, let's take a look back at r prime of t and let's try to think about what could I have possibly plugged in for t that would have created a vector that could have pointed to this point. I actually think this is really, really easy. Take a look at the final component here. I need the final component here to become pi over 2. So I think I need t to be equal to pi over 2. And if I quickly double check all of the other components, I'll see that they do indeed come out as a 0 and a 1 respectively. Okay, so that means that up here, I arrive at this exact point when t is pi over 2. Okay, this is good news. Now I can go ahead and find the direction vector for my line. Okay, so I'll say a direction vector for our line is given by r prime of 2. Right? I would need to evaluate the slope formula, so to speak, at the specific spot where I want that line. And that's going to spit out for me, something like, say, this orange vector here. Right? It's going to get me that tangent vector. So let's see. If I went to my r prime and I plugged in pi over 2, notice I get the vector negative 2, 0, 1. So now I have my direction vector and I have my line. So I should be able to write out my actual line. I should be able to go ahead and say that my L of t, I can even write this as its own vector function, is going to just be my slope, so to speak, times t, plus my vector that points to my initial point, just like we did back in the section where we talked about lines. Of course, if you want, you could write this as just a single vector, right? That is, I have negative 2t plus 0. I have 0t plus 1, and then I have t plus pi over 2. You could also express this as x equals negative 2t, y equals 1, and z equals t plus pi over 2. All right, so what we're going to want to try to do now is to take a look a little bit here as to what's going on in the 3D plotter, right? How do I visualize what's actually happening with the tangent vectors on this actual curve? So let's switch over to the 3D plotter. Okay, if I switch over to the 3D plotter here, again, what I'm going to want to probably do right away is delete out this first function and go ahead and graph a space curve. Now the curve that I'm going to graph is actually the original curve on the graph. So I'm going to do a 2 cosine t, a sine t, and a t. Okay, if I graph this, I can see what I'm ending up with here. I can even zoom out a little bit. I'm actually ending up with a little spiral shape here. I'm even going to go ahead and maybe adjust my axes so I can see a little bit higher and a little bit lower on this function, right? But I have this spiral that's happening. What I now want to go ahead and do is to think about what's going to happen again as I begin to trace this particular function. If I trace this function, I can start to see some different things happening. Okay. First off, I'll notice again that I see a couple vectors that we've talked about before. First off, I have this blue vector that's pointing out from the origin. That's telling me, hey, if you plug in t as a negative 5, you're going to point to and produce exactly this point on the curve. But notice that I also have this black vector here. Okay? This vector is my tangent vector. And one thing you'll notice about the tangent vector is that it has a different length at different points in time. Its length appears to change, and it also points in different directions, right? If I was to go ahead and like spin my graph around, I can see exactly where this vector is, but that's my tangent vector. And so for us, we were interested in creating a tangent vector when we were at the value of pi over 2. What we could see is now we were dealing with this point on the curve, and we computed the tangent vector that was right here. We should then be able to see that the equation of the line that we created should merely just extend that black vector. So I'm going to go ahead and I'm going to graph another space curve, but I'm going to type in the equation of the tangent line that we generated, which had x equal to negative 2t, y equal to 1, and z equal to pi over 2 plus t. Notice if I do this, you can see that the line that I currently have is indeed going right through, you switch to constant color, but it is indeed going right through that vector. And if I merely just play around with maybe say the values of t that I use to graph this, I can get it to extend out fully in the other direction. So can you kind of see that? That's what we've created here. Okay. Now there's one other vector that's popping up in the picture here, and that's this green vector. For the moment, you can just kind of ignore that. We'll talk about that vector at a later point in time. But the cool thing here to notice again is that it was at exactly this point that we wanted the tangent line, and our tangent vector allowed us to find that direction vector for the line. Had we wanted to draw a tangent line anywhere else, we would have had to say move this vector and deal with it at another point in time, and then we could have extended and drawn a tangent line off of a different portion of the curve. So again, playing around and spinning this sort of stuff around in the 3D plotter can be really, really helpful to make sure that you fully understand what's actually happening in this 3D world.